going to be exploring the quantum technology roadmap. And there is, before I go into that, I'd like to actually introduce the research group at the University of KwaZulu-Natal, Durban, South Africa, which is where I'm based. And we are actually involved in both theoretical and experimental activities within the field of quantum physics. On the theoretical side, we're working on activities related to open quantum systems. We also use NISQ devices in terms of quantum computing. We're actively working on quantum machine learning and quantum biology. On the experimental activities, which is where I lead the experimental activities in the quantum research group, we're working on quantum optics, quantum key distribution, quantum plasmonics, as well as cold atoms. And today, I'm going to actually focus on the introduction to quantum technologies. I'm going to take you through a BRICS collaboration called QSAF that Prof. Tawari and myself is involved in and collaborating on. I'll touch on some funding and career opportunities in the field of quantum technology and photonics, and summarize by looking at a summary of quantum technology. So to kickstart this, I think a good idea is to look at the quantum technology timeline. And here, this comes out of a document that the OSA-ODA just published this year, which looks at the quantum photonics roadmap. And in this roadmap, they illustrate 3 types of areas, which is quantum sensing, quantum communication, and quantum computing. And in the quantum computing, we know that technology to date, we have ANILUS, so the D-Wave quantum computer. We also have quantum computers that are based on NISQ devices, which is this noisy intermediate scale quantum computers. And what you probably know is that quantum computing is really attracting a significant attention currently, as well as funding. And this is because of some of its possible security implications. If we have a full tolerant gate-based quantum computer, a universal quantum computer, then theoretically we'll be able to factorize very large numbers much faster than any classical computer. And what this will result in is undermining current public key cryptography methods such as RSA. On the quantum communication sideline, we know that quantum random number generators as well as point-to-point quantum key distribution systems are commercially available. But in terms of progression of this technology, by the year 2035, what is predicted is that we'll have a quantum internet. And before that, we see a lot of development in intercity as well as intracity quantum communication links. In terms of quantum sensors, this technology area has advanced much faster, I guess. There are availability of these devices commercially, and quantum sensors basically looks at enabling high performance sensors, and here we'll be really using these kind of technologies for GPS navigation systems, for medical imaging, for atomic clocks. And so this is where the technology is moving forward in terms of this timeline. Now, we hear a lot about the 4th industrial revolution. In the quantum field, we're actually experiencing the 2nd quantum revolution. And the 1st quantum revolution brought us technologies such as lasers, diodes, and transistors, which is interesting because this year we are celebrating 60 years of the laser. What is more important is that the technology of the 2nd quantum revolution, which is quantum computing, quantum metrology, as well as quantum communication, is dependent on the technology of the 1st quantum revolution. And so we see that we are clearly shifting away from this classical approach towards a quantum approach, where we're looking at how quantum speed up or exploiting the field of quantum physics can improve technology. And so what I'm going to do for this remainder of this talk is focus on these pillars of modern society, and I'm going to basically look at quantum computing, quantum communication, as well as quantum metrology. And just to look at some of these applications, quantum communication, we know looks at secure transmission, and in the future we'll probably be looking at using these type of technologies for connected vehicles to secure critical infrastructure, as well as long-term protection of medical data or any data that is sensitive and requires protection and security. In terms of quantum computing, then we see that some of the applications of this area would probably be drug delivery, network optimization, looking at battery material simulation, as well as traffic optimization. In terms of quantum metrology, then we'll be looking at technology in this area that will influence clocks for synchronization, looking at trade and time stamping, as well as GPS-aided navigation. Now, if we have to touch on each of these areas, first and foremost, we would have to look at quantum computing. And quantum computing basically allows us to harness the superposition and entanglement properties of quantum physics to produce quantum computers that basically have the potential to solve certain problems much more faster than classical computers. So if we have to look at a classical computer, the way we encode information in a classical computer is that we encode information into bits, and this bit can either be a 0 and 1 or a 1. In a quantum computer, because we can make use of entanglement properties, we can make use of superposition. So we have the ability to encode information simultaneously into either a bit of 0 or 1. Now, and in this case, we create what is called qubits instead of just classical bits. Now, what we can say is since the late 1990s, so 1998, we started this development. There has been some development into producing qubits. And currently, what IBM has is 50 qubits on the cloud available for researchers to use. Google also has a 72 qubit machine, and Rigetti is said to have a 128 qubit machine. Now, in terms of these devices, both IBM, Google, and Rigetti all has NISQ devices, unlike the D-Wave system that works on annealing. So I'd like to actually look at some of these NISQ devices, and a lot of companies are focusing on the development of these NISQ devices. There are multiple ways to create these quantum computing gated-based systems, and one of the technology that has really taken off is superconducting qubits. And superconducting qubits are basically so quantum computers that are based on resistant-free current flowing in opposite directions through a superconducting circuit that basically contains a Josephson junction. And in this case, the qubit states are controlled using a microwave as well as low frequency electrical signals. And this allows us to then control the qubits itself. Now, companies that are working on these kind of technology is IBM, Rigetti, Google, as well as Alibaba. However, some of the challenges with these systems is that they require dilution fridges to keep the temperatures at a very cold microkelvin regime. And some of them also have the challenge of short coherence times. So there are challenges with all these technologies. In terms of spin qubits, which Intel is working on, these quantum computers manipulate the spin states of electrons that are confined in fabricated quantum dots that are on silicon wafers. The other technology that has taken off a bit is trapped ions, and the companies that are working on this is IonQ, Honeywell, as well as AQT. The trapped ion approach basically uses suspended ions in an ionized trap, and this is done in an electric field in a vacuum chamber. Here you use lasers to cool and prepare the ions, and thereafter you can perform operations on these ions that are trapped in this laser-cooled system. Microsoft is working on topological chargers. Here they're looking at using quasi-particles such as Majorana particles to develop their systems. And here they look at maintaining the quantum state in a large cloud of electrons. Neutral atoms, this particular technology which is where cold quanta as well as atom computing is working on. Here, instead of using ions in to be trapped, we're using neutral atoms. They are trapped in a magnetic and optical field. And here you actually manipulate the atoms to perform gates for quantum computing. The next approach, which is the photonic approach, is referred to as using linear optical components to produce a quantum computer. And here we're looking at encoding qubits in light traveling through maybe planar waveguides or optical fiber. And here we see Xanadu really working towards developing a photonic qubit quantum computer. You also have PsiQuantum as well as Okra computing. So there's a lot of development here. And in terms of photonic qubits, you can use discrete single photons, discrete states such as single photons or squeeze states to produce photonic qubits. Here I just show a case, the roadmap of IBM, to illustrate some of the uses of quantum computers. Now, one of the most important ones is that quantum computers theoretically is able to leverage Shor algorithms to basically break our common public key cryptography methods such as RSA. But the automotive and pharmaceutical industry is also exploiting the advantages of quantum computing. And there we see it in the terms of drug delivery. So for an example, a pharmaceutical company such as Biogen is actually utilizing quantum computers to look at the drug delivery process. Also, companies such as Volkswagen is using quantum computers to simulate various material options for batteries for the electrical vehicles. So we see that quantum computing is going to find its uses in many sectors such as manufacturing, healthcare, financial, distribution and logistics, as well as chemical and the petroleum industry. This further also looks at different scenarios such as usage in quantum computing, use of quantum computing for optimization, which I think is going to be one of its core uses, as well as for machine learning and artificial intelligence. So that actually introduces quantum computing and where the field of quantum computing is going, some of the devices we currently have and where their usage can be found. The next pillar that I'm going to look at is quantum communication. And before going into that, I'd like to illustrate what our conventional encryption technique is based on. And this is a very mathematical approach, the inability to factorize large numbers. However, if we have a quantum computer, a universal quantum computer, then theoretically, some of our current encryption techniques such as RSA or elliptical curve cryptography becomes vulnerable, and they can in fact also become obsolete. And it is for this reason that a lot of research is going into quantum communication, and this has been the case for the last 36 years, that a lot of research is going into developing alternative security methods such as quantum communication. Now, unlike conventional encryption methods that makes use of mathematical algorithms, quantum communication makes use of a physical system to encode information. Here you use a quantum carrier in the form of a single photon, and this is transferred through some optical medium that can either be free space or fiber, and this is then the quantum channel. And in this way, you can create a secure key that can be used to encrypt data. So the way this works is you have a transmitter and a receiver. You thereafter have a quantum channel, which can either be optical, fiber, or free space. And the whole aim is to distribute single photons that are encoded in either 0 or 1 through phase or polarization from the transmitter to the receiver. Once both share a key, then it undergoes post-processing where you undergo error estimation, error reconciliation, or privacy amplification. And this is done on a classical channel in order to produce a key that can then be used to encrypt data. Now, in terms of the technology, in terms of research and commercialization timeline for quantum communication, as I pointed out already, these devices in terms of point-to-point QKD devices are currently available on the commercial market. However, one of the problems is that they are still very costly. And they also have technical challenges. So they are used very modestly in the market at the moment. But in terms of development, quantum random number generators are available on the market, and companies such as ID Quantique is selling these devices. Fiber-based QKD devices are also available on the market. However, there is this movement towards satellite-based quantum key distribution, as well as intracity quantum key distribution, in order to develop what is known as a quantum internet. Now, if you have to look at the quantum internet, the underlying functionalities is developing this quantum key distribution network. And in that case, we would need to have to develop a network that is based on a hybrid system of free space and fiber-based quantum key distribution, which also includes satellite-based QKD. Now, if we have to look at requirements of developing a quantum communication system, we would have to break this out into a preparation state, a preparation system. So a way to actually generate single photons, which are your quantum carriers. Then you'd have to apply an appropriate encoding method, so either polarization or phase, to encode the single photons to carry the bits of ones or zeros. You would have to transmit it through some medium, which is either free space or fiber, and detect this using single photon detectors. Thereafter, we have the post-processing in order to eliminate any errors in the key, which then can be used for encryption. Now, in terms of detectors, there are a lot of progress in this area of expertise. We have single photon detectors that are avalanche photodiodes, as well as superconducting nanowire single photon detectors to be used for discrete variable QKD. And in terms of continuous variable QKD, we have homodyne detectors. So there are established detectors available on the market for developing or for generating these keys or detecting the keys during this whole quantum key distribution process. In terms of single photon generation, one way of actually generating single photons is to take a laser source and just attenuate it to the single photon regime. And in this case, we can do a prepare and measure QKD system where we prepare the single photons and transmit it from the transmitter to the receiver through the channel. The other approach of generating single photons is through the process of spontaneous parametric down conversion. In this case, we can generate entangled photons. The way this can be done is to pump a nonlinear crystal. This allows us to generate entangled photon pairs. One will be the signal, the other the idler, and we can use this as to encode information and to pass through a quantum channel. In this case, this is an entanglement-based QKD scheme where the single photon source can either be sitting with the transmitter, such that one photon is measured locally and the other is sent through the quantum channel, or the single photon source can be independent of the transmitter and receiver, such that a photon goes to the transmitter as well as the receiver. And so this is the way to generate single photons. Now, these techniques have been used in quantum communication links. And here I'm just going to highlight some of the key links that the scientific community knows very well. However, there are many links that have been developed over the years. And what I'll do is bring your attention to this recent review paper that was published in Modern Physics, the Journal of Modern Physics, that looks at all the different quantum communication links, and it is written by the group of J.W. Pan, and it was just published this year. In terms of free space links, we all know the well-known link that was published or implemented in 2007 by the group of Urson and Anton Zeilinger. This was a QKD link that ran 144 kilometers between the La Palma and the Tenerife Islands. Here they look at using a single photon source that was based on entanglement. They measure one of the single photons in the pair locally, and they transmitted the other photon through the free space link of 144 kilometers. The well-known satellite-based QKD net experiment or demonstration was done by the group of Pan. Here they launched the Miscus satellite, and they were able to implement QKD from a satellite to a ground station. They were also able to do an intercontinental video link from China to Vienna to demonstrate the use of the network. China is also leading in terms of fiber-based quantum communication. They have the 2,000 kilometer quantum link active, and this is based on a trusted node network. This basically has a 32 node based system between Beijing and Shanghai, which runs 2,000 kilometers, and this allows them to transfer single photons and generate encoded keys along this distance. There's also a lot of effort going into generating QKD systems on chip, where they use waveguides to transfer the qubits across from the transmitter to the receiver. Recently, there's also been a lot of usage of machine learning in quantum communication. And machine learning is basically a data-driven decision-making process, where the approaches is that you can use supervised learning, unsupervised learning, as well as reinforcement learning. And just to go through these three approaches, in terms of supervised learning, basically you have your data set, and in your data set, what you want to do is you want to map your inputs to an output. Except your data is labeled data. So what you're trying to map is actually embedded in the data that you use as your training set. In unsupervised learning, this is unlabeled data. Basically, in this case, you try to classify data based on pattern recognition. So here we see a mixture of data points, and what we're able to do is use supervised learning to classify it into its color-coded regions as its output. The other method of machine learning is reinforcement learning. And in this case, it's an agent-based system where you have an agent and it interacts with the environment. And the whole aim is to maximize the reward in the system. So you get a cumulative reward-based system. What we did is we used supervised learning and we applied it to a quantum communication based system, or we're applying it to monitor a quantum communication based system. What we did was, because we implemented this internal to the lab, we created our atmospheric turbulence, so we simulated our atmospheric turbulence based on Kolmogorov theory. Now, what you know is if you take a laser and you pass it through an environment that is has atmospheric turbulence, what you expect is that this laser field will undergo optical deformation. And I apologize, but this video seems to not be able to play right now. But what happens is the Gaussian field can undergo optical deformation. And by doing this, what we can do is we can actually measure this optical deformation. And this is done in terms of the star ratio, where we look at the intensity of the field before the atmospheric turbulence as well as after the atmospheric turbulence. And this then relates to the atmospheric turbulence structure constant Cn squared, which allows us to control the strength of the atmospheric turbulence. So what we did in the laboratory is we simulated this atmospheric turbulence, and we then embedded this simulated atmospheric turbulence into a single photon source that passes through our quantum channel. And in doing so, we thereafter produced or implemented a quantum state tomography, which allowed us to reconstruct the density matrix. We produced this for 102 density matrices at various turbulence strengths, so having various star ratios. We thereafter applied random forest, which is one of the supervised learning algorithms, and we tried to predict what is the atmospheric turbulence in the data that we have. So just to go through what is random forest regression, basically if you have a data set, then you have a number of decision trees. So you have an ensemble of decision tree. And at each decision tree, questions are asked to partition the data to allow you to predict the outcome. And in our case, we're predicting what the star ratio is, which will allow us to determine the strength of the turbulence in our quantum channel. What we're able to do is that through this method, we predicted with 95.56% accuracy our star ratios within our quantum channel. And we measured the error using MAPA, which is mean average percentage error. Now, ideally, in an ideal case, you would want your MAPA to be 0. However, a, a non-ideal case is always what happens, and you always have noise in the system. So here we were able to very easily predict what the strength of our atmospheric turbulence in our quantum channel is by just using machine learning algorithms. Now, this is just one approach of using machine learning to quantum communication. A lot of groups are using machine learning to look at improving the post-processing techniques in quantum communication, also specifically for continuous variable QKD, where noise is a big problem in the transmission as well as the post-processing. What we've also done is we've used machine learning for quantum communication to look at classifying high-dimensional states, so states that carry orbital angular momentum. And we were able to very significantly predict or classify orbital angular momentum states using machine learning. So there's really this drive now of actually embedding machine learning into quantum communication systems. The next area or pillar that I'd like to look at is quantum metrology. And in quantum metrology, as mentioned, here the focus is quantum sensors. And one of the technologies that we look at is atomic clocks. And atomic clocks basically uses the hyperfine transition of atoms as a frequency reference, which allows them to derive the standard time. Here also we can look at GPS using atomic systems for GPS navigation. In this case, using precision time measurements is critical for GPS systems, and so we can use this to determine accurately the distance between satellites as well as a ground receiver. In terms of imaging or brain imaging, magnetometers using either NV centers or atomic cold atom systems can be used to actually very sensitively measure the magnetic field of the electric current in the brain. And this will allow us to study epilepsy or Parkinson's disease or even dementia. So there's a lot of direction towards developing quantum sensors because there's applications that can be used to further enhance current technology. In terms of developing some of these core technologies, we will have to first develop a cold atom system. And I'm just going to walk you through the different procedures to developing a cold atom system. So the first part of the system is to mode lock to a hyperfine energy level. And this will be dependent on what type of atom you're using. So in our labs, we use rubidium atoms to trap within our cold atom system. And here you have a cooling and a repump laser that undergoes a saturation absorption spectroscopy process to allow you to mode lock to a hyperfine energy level of the rubidium 87 or 85 atom. You thereafter have to create an ultra-high environment in the vacuum chamber in which the trapping is taking place. And to do this, we control this using either two pumps. The first pump is a titanium sublimation pump, as well as an ion pump. Through these two pumps, we're able to control the environment in the vacuum chamber. The next part that you need to control in this cold atom system is the magnetic field. So here we have to use solenoids in an anti-Helmholtz configuration to control the magnetic field. We also have to create 6 beams that allows you to trap the atoms at the central point of the field. In this case, we use a 3-beam retroreflector trap. So we have a beam that passes into the vacuum chamber and then is retroreflected back into the chamber. And this allows us to then create the 6 beams to trap the atoms within the chamber itself. So this system in our laboratory, here's our saturation absorption system, here's your cooling laser and your repump laser. This allows you to mode lock to the hyperfine energy level. We have tapered amplifiers to ramp up the energy or the power of the laser field. We then have our pumps, our titanium as well as our ion pumps, in order to control the ultra-high vacuum environment in the vacuum chamber. And here we're able to trap rubidium atoms in the chamber itself. You see here the solenoid in solenoids in an anti-Helmholtz configuration, and we were able to successfully trap 10 to the 8 atoms in this magnetic optical trapping configuration. And so we are actually looking for collaboration on this project. So if you are interested in collaborating or you're interested in working on cold atom system, please reach out to me and I'll be happy to speak to you about further collaborations. Okay. The next part I'd like to introduce you to is a project that we started through a BRICS collaboration. And this is also in collaboration with Professor Manish Tiwari. And this is to develop a quantum satellite and fiber communication network. And this is a project that started only this year and is going to run for the next 3 years. Basically, our partners for this project is on the South African side is myself and Professor Francesco Petroccioni. Both of us are from the Quantum Research Group at the University of KwaZulu-Natal. On the Chinese side, we have Professor Zhuan Yin, and she's actually one of the lead researchers on the MISCUS project, which is the satellite-based quantum communication project. On the team from India, we have Prof. Manish Tiwari, and his area of expertise is photonic crystal fibers. And on the Russian side, we have Prof. Anton Bodin, who works has fabrication facilities to fabricate these photonic crystal fibers as well as novel fibers. And what we want to do is this global development of quantum internet is actually dependent on getting satellite-based quantum communication live. And so a lot of countries are now investing on the development of satellite-based quantum communication. So through this BRICS collaboration between Russia, India, China, and South Africa, we want to make use of the MISCUS satellite to develop a quantum network. This will involve setting up a portable ground station within the different countries that are involved to allow us to do an intercontinental quantum link based on satellite-based quantum communication. Furthermore, we also want to extend this to a fiber-based quantum system. And in South Africa, we plan on developing this such that we use the existing Sunrun network within South Africa to link through using the dark fibers between 4 of our major cities, which is Cape Town, Durban, Johannesburg, and Pretoria. So this is some of the aims of this BRICS collaboration. Also, in terms of the photonic crystal fibers, we want to actually look at using photonic crystal fiber and modeling this to actually transfer states carrying high orbital angular momentum or high dimensional states. Now, high dimensional states or states carrying orbital angular momentum are unlike Gaussian fields, which has a planar wavefront. They actually have a helical wavefront. So you take a Gaussian field and you convert it to a field, a wavefront that is helical, such that you have various orders of orbital angular momentum. Now, theoretically, these fields actually span an infinite state space. Experimentally, they're only limited by the optical devices used within the system. And so this is one of the aims, as well as the BRICS collaboration through the group of Prof. Manish Tiwari and his collaborators to actually see if we can produce higher order fields beyond 26 modes to pass through photonic crystal fiber. There are a lot of funding opportunities as well as career opportunities in the field of quantum technology. And I pulled this out from the OSA OIDA document, which basically looks at some of the investments from countries as well as government. So you see that there's a lot of investment from the US, 1.2 billion over the next 5 years. Canada has put in 1 billion Canadian dollars as well over the last decade. The European Union, through the Quantum Flagship Project, has budgeted 1.1 billion euros over the next 10 years. China is investing a lot into quantum technology. The UK as well, 1 billion pounds, and this has been an investment since 2013. Japan over the next 10 years is also investing 30 billion yen into the development of quantum technology. So there's really a lot of investment now going into the development of quantum technology. There has also been a lot of companies now investing in quantum technologies, as well as a lot of startups. And here I just pull out a few companies that are working on quantum computing as well as enabling technologies. Also, some of the startups that are looking at using these devices to focus on using quantum computing for applications. And here, Protein Q is a startup in Canada, but it's actually a student that got his degree at UKZN in South Africa and then moved to Canada and started his quantum startup. And he's doing quite well in the field. In terms of quantum key distribution, we know our key players, IG Quantique, but over the years, there's also a lot more startups in this area of research and development. And so there's also a lot of buzz now into the development of quantum technology startups. I'd like to actually use this opportunity to promote a few positions through the BRICS as well as the National Integrated Cyber Infrastructure Systems, Security Systems funding that we have. And we are looking for PhD and master's students. So we have 4 positions available, 2 PhD and 2 master's students. So if you are interested to work in the quantum satellite and fiber communication project, please feel free to contact me. My email address is ismaily@ukzn.ac.za. Okay, to end this talk, I'd like to actually look at a summary of quantum technology. And to do this, I'd like to touch a little bit on some of the milestones and the metrics. And I focus on the 3 areas that I've been going through this presentation, which is quantum sensing, quantum communication, as well as quantum computing. In the field of quantum sensing, there's been a lot of progress to date. And however, the performance is actually one of the reasons it stagnates is due to cost, as well as integration. And so a lot of these systems now is trying to be miniaturized sensors, which means it has to go towards on-chip. And so this is where the metric and future vision of this area is, to develop these systems more towards a miniaturized system sensors that are on-chip. In terms of quantum communication, we're moving towards quantum networks. However, one of the challenges is quantum repeaters as well as quantum memories. And the reason that we need this is because we need to actually scale these systems up in terms of distances, so increase the distances and improve the key rate. In terms of quantum communication, quantum computing, we want to move towards a fault-tolerant quantum computer, but in order to do this, we need to improve error correction as well as logical qubits. So there is this advancement towards advancing progress to requiring more funding for scaling as well as to support research and development. There's this drive towards improving hardware as well as software, and actually improve this, the skill sets of quantum technology, as it is a scarce skill set in some countries. In terms of summarizing the quantum technology in terms of optics and photonics are one of the core enabling elements of quantum technologies, as many of these systems require very precise control of light. And so some of the areas that we have to look at is the fact that lasers, single photon sources, which are also entangled, single photon detectors, homodyne and heterodyne detectors in the case of continuous variable QKD, fiber integrated and photonic based systems and waveguides so that we can move on chip. Modulators, we also require transducers and converters, as well as memories and quantum repeaters. So there's a lot of requirements in the different areas. So in terms of quantum sensing, quantum computing, as well as quantum communication. And there's this drive to develop all these technologies. Now, in terms of the laser technology, this is required across all the various areas of expertise. But this is also technology that has really advanced, and we're using lasers in a lot of these technologies already. But single photon sources are something that we're still working on. The technology is there, but they're not as efficient. And so these are areas that are still require some advancements. there's a lot of advancements required in terms of memories and repeaters for quantum communication. In terms of quantum computing, it comes with its own challenges. So there's a lot of requirements in terms of modulators, in terms of networking these systems, in terms of improving the quality of qubits that we are able to generate. And so there's a lot more opportunities in the field into the field of quantum technology. And so with that, I'd like to actually end with saying that the community is actually beginning to recognize the importance of these types of systems and the development of quantum technology, and they're really trying to push and enable a full ecosystem of quantum technologies as they see it as the future of technologies. And so there's really this drive to push the technology over this timeline towards the next 15 years. With that, I'd like to say thank you, and I open it up for questions.